We're starting in on electric fields today. The date is March 16th, just a little past 7. All right. So let me just jot down some ideas here. Let's go over to here. Electric fields. So the concept of a field is not something that's intuitive that people understand when they're first told about it. And the reason is because we don't see them. We don't see fields. These fields are these things that exist in our own world, in our own rooms, in our own stores, and they exist outwards in outer space, near stars, near galaxies. And these things are ways for one object to communicate a force to another object without touching it. So for example, like the Earth and the Moon, we know they pull on each other. They talk about a gravity, gravity and gravitation, and that's a force, and that the Moon and Earth pull on each other. But interestingly, even though Isaac Newton had uncovered the idea that he kind of developed the idea of the force, and that the Earth and the Moon pull on each other, and he certainly went well beyond that and developed a whole equation, that you learned earlier as Newton's law of universal gravitation. That now, when he said in the 1600s, I know how to calculate how much force the Earth and the Moon pull on each other with, and he knew that it depended on how far apart they were, r in the denominator, and then he knew it depended on how much mass each of this, the planets have, the Sun and the Earth. Those are the numerator. The point is, if you could go back in a time machine and ask Isaac Newton, how does that work? You'd first, of course, say, very impressive. You have an equation for calculating how hard the Moon and the Earth pull on each other. But, Mr. Isaac Newton, how does that actually happen? How can the Earth pull on the Moon when they're not touching each other? And he would respond that he doesn't know. He didn't understand how it worked. He just know it happened. And he said evidence for that was that the Moon goes around the Earth. So he knew that it was true, and he developed an equation to calculate that force, but had no understanding of how it actually worked. It took 300 years or so before Einstein came along in the early 1900s and finally developed the idea of the gravitational field, that there were curves in space, that planets can actually curve, that space isn't just this emptiness that we think of it as. It took an Einstein to say, okay, even though we can't see it, when we look into space, we just think of air. It took Einstein to say, well, actually, in outer space, space actually has these features, these curves and bends, and that when you're near a really heavy planet like Jupiter, Jupiter bends that space significantly. And that's the idea of the gravity field, that it surrounds the planet, Jupiter and all other planets. And that field, Jupiter's gravity field, extends into outer space, and it allows Jupiter to pull on its moons without touching those moons. It can still pull on them, right? And it's this idea of a force field. You've probably heard of that even as a kid. You've heard of force fields like in Star Wars and stuff?
Yeah.
The idea of the force field is this idea that, like in Star Wars movies, that I could just use the force and push you. Even though we were 10 feet apart, I can kind of just use my hand and focus, and all of a sudden you'd go flying across the room, right?
Yeah.
That really is the essence of the force field, that I could apply a force to you without even touching you. And in fact, that's exactly what gravity does. Planets pull on each other through their fields that we don't see, but we know they exist in outer space. And it turns out magnetism, we know magnets can push and pull on each other without touching each other. Turns out there's a magnetic field that surrounds magnets. And then also with electricity and electric charge, there ends up being this electric field that surrounds them that we can't see with our eyes because we're just not able to see it, but it's there, and we know we can measure it, and we know that when we put a proton next to another proton, we know that even if they're not touching, they repel. And when you get this idea that there's actually a field that surrounds the original proton that was sitting there, and when you drop a new proton in that vicinity, that proton, the original proton, its electric field will push proton that you drop there, even though they're physically not touching, the field is what communicates the force between them. And that's the concept of fields in general. So that's a background on fields. So the electric fields have shapes, and they radiate directly out and away from all positive charges.
I'm not really seeing the screen.
Oh, you're not? Okay. I don't know why, because I think it says you're in the conference.
Might have been frozen on my side.
Were you ever seeing the screen at any point?
I mean, like, I'm seeing it, but, like, this is showing, like, this thing reconnecting. So, yeah, I think it's just my something on my profile.
Okay, I'll wait and let me know if it reconnects.
Oh, okay, yeah, so I have no internet connection. Interesting. Give me a sec, I'm sorry.
It's all right.
I should be good now.
Okay, can you see everything?
So I'm just writing my name. I sent your request.
Oh, I see it now. Okay, let me. Okay, are you in now?
Yeah, I got it.
Okay, so I'm just jotting a few notes down. This is the visual. You would see it in your textbook. They show pictures like this. They're trying to indicate that these fields that we know do exist, even though our eyes don't perceive them, that the shapes of these electric fields that surround positive and negative charge have the shape that's called a radial field lines. So they use the word radial, means it extends from the source radially out along a radius. So like if this was, I don't know, a positive charge here, and you imagined a circle surrounding it, the radius goes straight out, right?
Yeah.
And so they call those radial lines because they mimic the radius of a circle. And you can also think they're radial because that's what to radiate means. It means to extend away from in all directions in straight lines. So we call the shape of those radial. And they surround all positive and negative charges. Trying to think of the word I want to use. They belong, I guess is the way, I don't know how better to say it. They belong to the charge, which means it doesn't take two charges for these fields to exist. So what I mean by that is, if you imagined we emptied our universe entirely and only left one proton in the universe, it would be a philosophical question to ask, do these electric fields still exist in this empty universe that has just one proton? And from theoretical physics, it says that they would still exist. That it doesn't require a secondary charge to come into this relatively empty universe to create the electric fields. That those electric fields belong to the positive charge, and that even if he is all by himself in the universe, these fields would still exist. They'd radiate out away from him, and they'd go all the way out into infinity, infinitely far.
Oh, okay, I see.
That makes more sense, probably.
Yeah.
And so another important part is that the strength, and actually I'm going to start referring to it as E fields. That's very common for physics people to just refer to these in short, E for electric fields, E fields. So the E fields, there it is. What the heck? The E fields strength diminishes as you get further away. So this force field, this electric field that allows this proton to push on other protons or electrons without touching them, that ability to push diminishes if those new other charges are far, far away. It'll still, if you drop a proton really far away from another proton, they'll still push on each other, but with just a little bit of force, maybe 2 newtons or 3 newtons. But if you bring those 2 positive charges extremely close to each other, the force that this force field, this electric field, would push on the other proton that you drop down would be much stronger if it was a very close distance. So E, at these points here, if we call them E1 and E2, E2 is greater than E1 to indicate that it's stronger when it's close to the charge versus weaker when it's further away. Does that make sense?
Yeah.
And E, the capital symbol E, represents how strong the electric field is. And it's actually a vector, and I'll tell you more about that. E represents how strong the E field is. Okay? And I'll tell you the units and all that stuff. I'll get into that later. I'm just trying to get you a conceptual understanding of everything. So yeah, any questions so far?
No.
Okay. So I'm going to erase the board. Okay. So I'm going to show you how you determine what's referred to as the magnitude and the word magnitude is really just going to represent strength, how strong the field is.
Yeah.
Do you know what they mean in physics by a point charge or a point mass?
A single point is a charge.
Yeah, exactly. So what that is an approximation to assume that the charge is so tiny that we can almost approximate it as existing in just one tiny point. Like we wouldn't approximate the Earth as a point mass because we know it's not just as small as the point of a pencil. It's a giant thing, right? But there are things, especially in the atomic world, that are so tiny that we live on a macroscopic scale. So compared to us, they're so small we consider them point charges because they're literally tiny enough to just occupy just one tiny space. Okay, so in this problem, this is a very common starting point. We'll start with, let's say, a positive charge, and we would say that there's some point P, and that point P is some distance away from the charge R. And we're interested in, and this is an empty point, just an empty point in space. But we know that his electric field extends in all directions outward, right?
Yeah.
And so will one of those electric field lines pass through the point P that I've written there?
No.
If they go in all directions, will one of them go directly through this point?
Oh, yes, it does.
Yep, exactly. And so I'll draw that another idea or another version of that. If this was point P, this electric field line right here would go right through that point and extend outward, right?
Yeah.
And this is now a vector that we're using. Oops. Sorry, 1 second. So E, and it's specifically capital. I know I'd write everything in capitals, but it's in the book textbooks. It's a capital E. So E is a vector that represents the strength, which we refer to as magnitude, and direction of, we're going to call this charge over here. Do you remember the symbol, the letter symbol that we use for charge?
Q.
Q, yep. So I'm just going to call him Q. So this vector that represents the strength and direction of, I'm going to write Q's E field. Because does his electric field have a direction that it's pointing based on that picture on the right?
Yeah.
It does, right? It's a very specific direction. And we know that if we drop the positive charge right at that point P, which way would that positive charge go?
It goes up, right?
Yep, up and to the right, which is the direction of his electric field, right? Of Q, the original charge that created that field.
Mm-hmm.
His direction of his field is in that direction of that arrow. And if we drop another proton at that point, it will go in the direction of that arrow, right?
Yeah.
So E now, again, since it's a vector, and all things in physics that are vectors have both magnitude and direction. And the magnitude is interpreted as how strong the electric field is that belongs to Q, that's in the center of the screen, at that position P. And it has a strength and it has a direction as well. And so in magnitude, you remember this is the magnitude symbol, right?
Mm-hmm.
Magnitude of Q's E field at point P. So it turns out that that magnitude at this point P here that I've drawn is proportional to how much charge he has. So if you put more charge in the center of the screen there, then the strength of the electric field at point P would get stronger.
Yeah.
And if you had less charge at the center of the screen there in the drawing, then the electric field at point P would lessen, weaker,
Mm-hmm.
right? So those are proportional to each other. And that makes sense with magnets. You know that if you have, a large magnet, does it normally have a stronger magnetism than a small magnet?
Yeah.
Yeah, normally that's true. And so you can think of the large magnet as a collection of a whole bunch of tiny magnets all stuck together. So when they build that larger magnet, they're just adding more magnetic pieces of metal to each other, and the strength of the magnetism goes up as a result. Those are proportional in magnetism as well.
Yeah.
And so remember, though, that I pointed out that if you get further away, what happens to the strength of the field? It diminished, right? And so that's why in the second proportion, R would go in the numerator or the denominator?
Go in the denominator.
Yep. And it turns out, again, it's a square, just like Coulomb's law. This is going to have, you're going to see a lot of similarities with what Coulomb's law is. So a huge amount of similarities. You remember Coulomb's law was the inverse square law, right? Jeremiah?
Yeah.
So Coulomb's law utilizes the inverse square law, which means that if we're looking at forces now, the electric force, if you double the distance between the charges, by what factor does the electric force change by? If you make them get 2 times further apart.
Change by 4.
Good, you remembered that. Yep, because of the square, right?
Yeah.
What if they get 3 times further apart?
It would be by 9.
Yep. What by 9? Stronger by 9? Stronger force by 9 times, or 9 times less strong?
Stronger force by 9 times.
Say it one more time.
Stronger force by 9 times.
If we make them 3 times further apart.
Oh, further apart. Oh, then it diminished by 9.
Exactly. Good. So it's the same idea that we're seeing here, that the strength of his field that I'm drawing here still holds those same proportions that we just talked about.
Yeah.
So if R increases times 2, then the strength of his electric field goes down because they're inversely proportional, times 2 squared, which will be 4 times weaker.
Gotcha.
Right? That's the reason that the force ends up being 4 times less. It's because the field itself is 4 times less. And the field is what communicates that force between the charges without them touching. So if the field gets 4 times weaker, when it finally applies a force to something you drop there, the force will be 4 times less. Because the field is 4 times weaker. Okay, so these are the only proportions, the 2 that I've written here. This one and the other one next to it. And so when things are, when you derive equations or create equations, there's always something that remains constant. We call that the proportionality constant, right?
Yeah.
So can I erase the right side of the screen?
Yeah, you can.
Okay. So to combine these 2 proportions into one equation, the strength of the electric field at some point P in space will be equal to however much charge that is creating. Remember, this is the charge that creates the electric field. And the E field is what we're referring to right here, right? So these are properties of that charge. How much charge that charge has is proportional to how strong his electric field will be at any given point in space, right?
Yeah.
And then divided by R squared, remembering that, again, if this was point P, R is just the distance between them. Between the point that you're interested in looking at and the source of the charge, Q. So far, so good?
Yeah.
But since there's a proportionality constant, that proportionality constant is the same constant that you had from Coulomb's law, K. Remember that?
Yes, I do.
So that is
6.25 times 10 to the 9th, right?
so actually it's 9 times 10 to the 9th.
9 times 10 to the 9th.
That's okay. Electricity constant. Okay. Any questions about that?
No.
All right. I'm going to now erase the left side of the screen. And now we're gonna use it. In fact, actually, let me peek at one of your problems and see if we can just use it on one of your problems. That makes more sense. Let's see here. No, I guess we're not quite ready. Let me see, 24. Yeah, we're not, so they didn't give you any like really easy ones. So I'm just gonna make one for you to try, and then we'll build into your problems on your homework.
All right.
So let's say this was, and do you remember the unit for charge?
Yeah. Q, right? Yeah.
So Q is the symbol for the quantity. This is the quantity.
Unit is Coulomb.
Yep, good. Coulombs will be the unit for just the international standard unit known as SI. for electric charge. Named after Coulomb. Okay, and so let's say this charge is 50. Do you remember how to interpret MC, lowercase m, capital C?
Yes.
What would the words be for m, lowercase m, capital C?
Meters. No.
It's okay. Try again. Like, for example, kg, I'd say the words for that are kilogram.
Microcoulomb.
Good guess. That's the most common guess. Remember, M stands for milli. And I know,
Millicoulomb?
yeah, I know milli.
Most. You did right now.
That's all right. Most people would say milli has something to do with million because it seems that way, but this is actually milli.
Millicoulomb.
Yep. Oh, hard time writing this. 1 second. Milli. There we go. Millicoulombs, and that means 1/1000th of a coulomb. Okay.
Yeah.
Something that's in the milli, like a millimeter, is one millimeter is 1/1000th of a meter. So how would we write that in scientific notation? 50 millicoulombs. Because when we get over to our calculator, we're going to have to enter a number in, and we can't type in, milli. We have to turn it into a number.
5 times 10 to the.
Let's just start with the number 50 because that's what it is. 50, then millicoulombs. So you write 50, and then how do you write millicoulombs? Times 10 to the
-3.
Yep, exactly. If your teacher forced you to put that in proper scientific notation, which is a number between 1 and 10, what would it be?
5 times 10 to the -4.
Yeah. So, 10 times 4. Actually, well, you have to go back 3, right?
Yeah, you have to go back 3.
So, you sure about that? So it would be, be 0.005 is that number. That's what 50 times 10 to the -3 is. So it'd be 5. What am I saying? 50 times 10 to the -3. Oh, I'm sorry. I was backwards. It would be here. Yep. So it'd be 5. Yeah, that's why I thought it was you were doing it the reverse. So let me explain what I'm trying to say. Let me get rid of this. Or let me just get rid of all this. So if I wrote that out, if I wrote the number 50 and put the decimal here, and then I'm just going to add some zeros behind it, right? So if we look at the original number, 50 times 10 to the -3, I would shift this decimal over 3 times, right? 1, 2, 3. And what number am I left with? 0.05, right? And so if I wanted to think of that now as the number 5, which is over here, the decimal, how many decimals do I have to shift to get back to that one?
3. No, 3.
1.
No, 1, 2.
1, 2, right? Which is why it would really be 5 times 10 to the -2. Yep. Now, do you have to go through thinking about that? I mean, no. I mean, if the teacher forces you, I don't know if your teacher does that. But in your calculator, you just type 50 times 10 to the -3. And you're done.
Yeah.
Right? Okay, so that being said, let's have you practice how strong is the electric field at this point. And let's say that it's directly above the charge. So it's directly up here, and then we have some point that we refer to, and we give you a distance. Let's say the distance is 5 mm. And now the question is, how strong is the field, and what direction is it in at this point here? So remember, there's the equation on the right that you'll use now to calculate the strength of that electric field.
Okay, so we plug in it's 50 times 10 to the negative third in for K.
So in for K will be the 9 times 10 to the ninth.
Not K, M and Q.
Yep, in for Q will be 50 times 10 to the minus 3. Yep. But
Multiply that by
you might want to try my...
to the minus, not negative 9 to the minus.
You might want to try my method, which was working out the denominator first and then storing it. Unless you want to try to put it all in at once. It's up to you.
No, that method actually worked better.
Just remember that the distance I've provided is 5 mm. What does that mm mean? The distance I gave you is 5 little lowercase m. What does that little lowercase m represent? What words go with that? What's that?
Milli.
Milli what?
Milli.
Mm.
Oh, millimeters.
Millimeters, yep. So what number will that be when you put it into your calculator? 5, and then milli is always what? Times 10 to the what?
Times 10 to the 3.
Yep, times 10 to the...
third.
Yeah, minus 3, right?
Minus 3.
Yep, because it's a number less than 1. So when you're putting that in for R and squaring it, I would recommend doing that first, and then just storing it. Seems to be an easy way to go about it. That way you don't have to write anything down.
R is where again?
R was 5 millimeters. So the charge that we're placing down on this drawing, the actual charge is right here, right? And he's a positive charge, and the amount of charge he has is 50 millicoulombs, right? And then there's some empty point, they normally refer to it as point P, for a point in space, and the distance from where this charge is all the way to that point is 5 millimeters. And that's what's going to be R in your equation, because R represents how far away that point is from the source of the charge. So in for R, the denominator is 5 times 10 to the minus 3, which represents 5 millimeters. But don't forget to square it. And then you can store that. Do you remember how to store it?
Yes.
So after it's stored, then you would just return your attention to the numerator. And you'd put in for K, 9 times 10 to the ninth, times how much charge are we dealing with Q?
Q, yeah.
And remember, that's the value 50 millicoulombs, which would be 50 times 10 to the minus 3. And then you're going to get that answer, and you'll just divide by x. You're going to get a large number, which don't be afraid of large numbers. This means that his electric field is very strong at that particular point. And you can always write your answer in scientific notation and round off to, looks like we'll have two sig figs here, or actually we have one.
Yeah, I got 1.8 times 10 to the 13.
As your answer?
Yeah.
What did you get for R when you squared R? After you squared it?
2.5.
Times 10 to the?
Times 10 to the negative 5.
Okay, I got that too. And then 9 times 10 to the ninth for the numerator. And and then that gets multiplied by 50 times 10 to the minus 3.
Yep.
And then you divide it by x?
Yes.
Okay, because I got different answer. I get 7 A whole bunch. It's a huge number. 758,981,278.
Times 10 to the 9 times 50 times 10 to the negative 3. I got the 45. Looks like.
1, 2, 3. Yep.
I got 450 million.
Yep. So I got 45 with 7 zeros after it.
Yeah.
And then you just hit divide by x. Are you sure you stored it as x?
Yeah. I stored it as x. 2.5 times 2.
Oh, I didn't store it as x. My fault.
Oh.
My fault.
Sorry.
Let's see here. 5 times. Oops. My apologies. Yeah, square. Oop. What happened here? All right, starting over. 5 times 10 to the minus 3 squared. All right, store as x. 9 times 10 to the 9th times 50 times 10 to the minus 3 divided by x. Yep, my apologies. So let me erase that. So I'm getting 1.8 times 10 to the 13th. Is that what you got?
Yes.
Okay. All right. So now it's, I think, a good time to tell you what the units are for that. I'm going to erase this. So the units for an electric field are newtons per coulomb. Normally just written N over C. So what that means is, let's just say, just so you can conceptualize what I'm trying to say, let's just say that your answer came out as the number 50. Okay? Jeremiah?
Yeah.
Let's say that when we just did this problem, we got E equals the number 50. That would be 50 newtons per coulomb. What that would mean is that if you dropped exactly 1 coulomb of charge at that point P, then how much force will it feel? 50 newtons. Because that's the nice idea of the units. It means that field that charge Q has created will deliver 50 newtons of force per 1 coulomb that you place at that point.
Gotcha.
If you place 2 coulombs at that charge, if you place 2 coulombs at that point P, how many newtons of force would it receive? Remembering the strength? How many? So the strength of his field, of Q's field, is 50 newtons for every coulomb that is placed at point P. So if you place exactly 1 coulomb at that point, that would push away, because pluses and pluses repel. It would move in the upward direction. And right when you drop it there, if it was exactly 1 coulomb that you dropped there, it would feel a force of 50 newtons. If you drop 2 coulombs there, it'll feel 100 newtons. If you drop 3 coulombs there, it'll feel 150 newtons. Because the strength of that field is 50 newtons per 1 coulomb that you place at point P. So it's a way of expressing how strong his electric field is, or it's a way of expressing how much force his electric field will push on another charge that you place at point P based on how much charge you put at point P. Because remember, Coulomb's law, which has is a way of calculating electric force, does it depend just on one of the charges or on both charges?
Upon both charges.
Upon both, exactly. And so the force that some new charge will feel if you place it at point P depends on how much charge you place at point P. Does it also depend on how much charge is at the I don't know, let's call this point A, I guess. Right here, let's call this point A. So when you drop some charge at point P, does the force that the charge feels at point P also depend on how much charge is at point A?
Yeah.
Yeah. And it also depends on how much charge you place at point P. Because remember, the electric force is equal to in the numerator, it's the product of their charges. One charge multiplied by the other charge.
Gotcha.
So let's try you one more time. let's say you drop half of a coulomb, 0.5 coulombs at point P. How much electric force would it feel?
25 degrees.
Yep, good. You got it then. Right? If you dropped 1/5 of a coulomb, 0.2 coulombs at point P, how much electric force would it feel?
5.
Good guess, but 1/5 of 50 would be.
How much is that?
That's all right. 1/5 of 50 would be 10. But I think you get it. You get the idea.
10.
Yep. So that makes sense.
Yes.
And also, in which direction will the original charge that's been creating this field that we've been talking about, in which direction does his electric field point at point P?
Upwards.
Upwards, exactly. Good job. Because all electric fields radiate out and away from positive charges, right?
Yes.
So let me do one last thing, and then we'll move on to building upon it. So if this was point P here, you would show his electric field as a vector pointing up, which you would refer to, if someone said, I want a direction, that would be at 90 degrees. Because remember, straight to the right is 0 degrees, right?
Yeah.
So the direction of his electric field would be up, which numerically would be referenced as 90 degrees. And then the strength of that electric field at that point P would be whatever we just got, I don't remember, 1.8 times 10 to the 13th.
Gotcha.
Newtons per coulomb. Which is huge, it's a lot. But it's because is 5 millimeters far away from that charge or close to that charge?
Close.
Very close, right? So it's the electric field we've calculated being so big, so strong, is due to two reasons. One is because we're really close to it, only 5 millimeters away. And two, 50 millicoulombs ends up being a lot of charge, a significant amount of charge. That's billions and billions and billions of protons all stuck in one point. It's a lot of electric charge. And so since you have a lot of charge, does that also create large, strong fields around it?
Yes, it does.
Yes, it does. So it's the big answer that we got for those two reasons. Okay, so now I'm going to erase the screen. All of your problems that I've noticed are involving two charges. And so I'm building you in that direction. All we've so far really talked about, more or less, was how to determine how strong an electric field is at some distance away from a single point charge. But now we have to tackle a little more complicated problem, which would be, let's say there's a positive charge here and a positive charge here, and we want to know how strong is the electric field at that point P. So this becomes more complicated, but it ends up being that we get to just reuse the same ideas just twice this time instead of once.
Mm-hmm.
So before I show you this problem, let me just give you a sense of something. Let's say you had a fan that was blowing, right? And you were going to place, I don't know, a feather over here. The direction of the wind is blowing to the right in my drawing, right? This is a fan. I'm just trying to give you an analogy so it makes sense. So the fan is blowing. Could we technically quantify how strong the wind is blowing at point P? Well, yeah, we would probably call that miles per hour, right? Wind is blowing at 20 miles per hour. That would be the magnitude of the strength of the wind. That make sense?
Yes.
And when we drop a feather there, which way would we expect it to go?
We drop a feather, it would go in the direction of the wind.
The direction of the wind. It would go to the right in my drawing, right?
Yeah.
Same idea that we're working with now with electricity. However, would it become more complicated if I said in my drawing that, oh, we're going to place another fan here and it's going to be blowing air this way. And now we're going to still drop a feather here, and notice one of the fans, the one on the right, is close to that point where we're going to drop the feather, and the other fan is much further away, and we're still going to drop a feather at point P, and we want to know which way it's going to go. Would that be more complicated?
Yes, it would.
It would. That's exactly what all your problems are. You'd have to say, well, okay, if I can work out how much force this fan is going to deliver, I can say this is some force from fan 1. Force from fan 1, I'll call this fan 1 on the left, and we'll call this fan 2 on the right, right? So maybe we say the force from fan 1 is 20 newtons. Well, what if we find out that the force from fan 2, the one that's on the right, well, that one's going to blow the feather which way? To the left, right? If we said the force from fan 2 is, 50 newtons, and we know that force is to the left, then you'd say, okay, oh, there you go. Are you back in?
Yeah, back in, yes.
So in my illustration here, you're saying we've got two fans. The fan that's on the right is going to blow the feather to the left. Does that make sense?
Yes.
And it's going to blow it with 50 newtons of force. And that other one that's further away on the left, well, that's blowing wind to the right, so it would technically blow the feather to the right, only with 20 newtons of force. Could we technically find out with this information which way the feather should blow, right or left, when we place it there?
Yes.
Which way would it go?
We go towards the right.
50 newtons of force to the left, 20 newtons of force to the right.
Oh, no, we go to the left.
You'll go to the left, because we would have to find out what the net force is, right?
Yes.
And we would call this one plus and this one minus, and we'd say the net force is 50 minus 20, comes out as, I'm saying that backwards, my apologies. 50 to the left is negative, right?
Yes.
This one's negative, and this rightward force would be a positive, and we would say, okay, minus 50 plus 20 is minus 30 newtons, so the net force is negative 30. We would drop a feather there, it should go to the left, right? That's exactly what we now have to do with the electric charge. We have to work out how strong is the electric field due to one of the charges at point P. How strong is the electric field due to the other charge at point P? And then we add those two electric fields together to see which direction it's pointing in, to get what's called the net electric field. So let me build on that now. So let's say we have plus 2 coulombs of charge here. We'll call that Q1. And let's say we have plus 2 coulombs of charge here. And let's say we designate point P right in the middle, okay? So that this distance is R, and that this distance is the same distance R. What is E, the net electric field at point P? So I want you to think about this one without necessarily doing any calculations. Just try to process what I've asked. Look closely at the values I've given the charges. Look closely at what sign the charges are. Are they positive charges or negative charges? And see if you could answer that question without really trying to do a whole bunch of calculations.
All right.
So at point P, right? What we're going to do is visualize what does the electric fields from Q1 look like. We know they radiate outwards and away, right?
Yes.
So which way will his field be going when it passes through point P?
Towards the right.
Towards the right. And I'm going to go ahead and call that E1 to indicate the electric field created by Q1. Does that make sense so far? Then we turn our attention over to the charge on the right. His fields are also radially going away in all directions. which way will his electric field go passes through point P?
To the left.
To the left. Will this electric field be stronger, the same strength, or weaker than E1? And why?
It would be equal to.
Exactly. It would be equal. So what is the reason for that?
Because what charges are +2 coulombs.
Yep. They both have the same charge. And what else?
And they're the same distance.
And they're the same distance. So no matter how strong one of their fields is, the other is going to be the same strength and magnitude, but in the opposite direction. And so what would the net E field be when you add those together?
It'd be 0.
Be 0, exactly. You would conclude that the net field there, and that's why you didn't need a lot of calculation, just concept really, to recognize that those two electric fields are going to cancel each other. And therefore, if you did drop a positive charge here at point P, you just try to take a proton out of your pocket and drop it right there, which way will it go?
To the right. At point P, it's nowhere.
Nowhere, exactly. It'll just sit there. Because the charge on the right is trying to push it to the left with some amount of force, but the charge on the left is trying to push it to the right with the same amount of force, and what would the force be? 0, and it would just sit there. It'd be like somebody sitting in a chair, one person's pushing that person to the right with 5 newtons of force, another person is pushing that person in the chair to the left with 5 newtons, the person doesn't move because the net force is 0. Right?
Yeah.
All right. But now let's make it a little more complicated. Not really more complicated, just more, it's the same picture, same problem, but just a little more challenging. Let's say this again is Q1, and let's again say it's +2 coulombs. But now let's say that this one over here, Q2, is 4 coulombs. And we do the same question. Here's point P, and the question is, these are 2 positive charges. Find the net electric field in magnitude and direction at point P. And point P, of course, is right here. So I'm actually going to just do this one for you just to show you, and then I'll let you try your homework one. Okay? So what we do is we say to ourselves the same idea that we did before. Which way we're first going to look at Q1. Which way does his electric field go as it passes through point P?
To the right.
To the right. So I'm just going to draw it in there like this and call it E1 with a vector symbol. Which way will charge 2's electric field move or pass? You know, which direction will it be pointing as it passes through P?
To the left side.
To the left. Will it be longer as a vector, shorter as a vector, or the same length as a vector as E1? And why? Well, yep, exactly. How many times longer? Good. Yep. It'd be exactly 2 times longer, which means that his electric field should be twice as strong because he's got twice as much charge, because those are proportional, remember?
Yeah.
E is proportional to Q. And so the stronger field that he has is not due to the distances. They're at the exact same distance, just due to his extra charge being twice as much charge, twice as strong of a field, right? And I'm going to call that E2. Put a little vector symbol over it. Now what we refer to as the net field as a vector is going to be E1 as a vector plus E2 as a vector. Okay? We just have to add the electric fields together, and whatever the leftover amount of electric field is, that's called the net field. And so what we do is we then, at this point, just stop and recognize, oh yeah, there's an equation. There's an equation for calculating how strong E is, right?
Yeah.
Yep. And so I'll write that down here. E in general, at least in magnitude, is always KQ over R squared, right? And so we can apply this equation I just wrote down once for Q1 to figure out how strong his electric field is, called E1. That will be a numerical value for how long this vector is. What sign would we apply to it, plus or minus? for E1
Plus.
plus. So we know that in our minds it's got to be to the right. We'll reference that as a positive. We can figure out the quantity by just using KQ over R squared, where Q will be Q1's charge, 2 coulombs.
Yeah.
And I'll have to provide you with a value for R. I haven't done that yet in this problem, but I'm just stepping you through the thoughts. And then we'll have a value for how strong E1 is. Then we would just apply the same equation to E2 and put in Q2. It would be K times Q2 times that distance squared and get a number for it. And that'll represent how long this vector is, E2. Which sign would we make it, positive or minus?
You make it positive.
Because notice which direction is E2 pointing.
Oh, so to the left. Oh, you make it negative.
Make it negative. And then when we have those two things as numbers, what will we do to find the net value of the electric field?
You would add them together.
Just add them up, and we're done. And if the net field comes out as a positive value, you know that the E1 must have been stronger than E2. If the net field comes out as a negative, then you know E2 must have been stronger. In our own minds, what must the net field be, positive or negative, just based on our drawing?
It was going to be negative.
It's got to be negative because why?
Because for a larger number, it was negative.
Exactly. There was 4 coulombs on the right and only 2 coulombs on the left. So
Yeah.
there's a larger pushing force in the leftward direction. So our answer in the end should come out as negative. So now what we'll do is I'll just show you the mechanics of solving that. I haven't given you any distances yet. So let me just write that in. And let me just look at your problems. Yeah, I'm gonna have to just practice. Have you practice. I could obviously make it easy to say 2 meters, 4 meters. But when I look at your homeworks problems, they're always distances are in centimeters or in millimeters. So I'm going to do the same.
All right.
So let's say it looks like a lot of your problems give distances in centimeters. So let's just practice that. So let's say the distance from the middle to the end is 25 centimeters.
Mm-hmm.
And the distance from this side all the way to the other side is also 25 centimeters, right?
Mm-hmm.
So now this is how we would move forward with it. We're applying this equation to find out how strong E1 is. So E1 will be K times Q1 divided by that distance squared, right?
Yes.
And remember, it just happens to be in this problem that they're equal distances from the center, right? But if that point was closer to one of them than the other, then you're going to have to distinguish. Normally what we do is, like for this one, we would call this R1 to indicate this is the distance that Q1 is from point P. And we would call this one over here R2 to indicate that's the distance that Q2 is from point P. Right now they're the same just because of based on the way we made the problem, but they might not be the same distances.
So to find Q1, it would always be Q1?
Yep, exactly, because electric field due to charge 1 is only depends on Q1. That's exactly right. We're trying to figure out how strong his field is at point P, and his field is proportional to his charge because he creates that field.
I see.
And so numerically, I'll do it over here, running out of space. But I'd put in 9 times 10 to the 9th for K. Times 2, yep. All divided by
25 squared.
Be careful with the units, though. What unit did we get distance?
Centimeters, I have to convert that. So is it 0.25?
You got it. Squared.
0.25 squared.
Yep.
And put that on the computer. I got 2.8 times 10 to the 11th. 2.88 times 10 to the 11th.
I'm sorry, 1 second. Yep. 2.88 times 10 to the 11th. So I'm going to write that in. 2.88 times 10 to the 11th. Since notice I'm expressing it as with a vector symbol. So that means I have to provide not only quantity or magnitude, strength of the electric field, but I also have to provide some sort of direction to the reader. Is this a field that's to the right or to the left?
To the right.
Exactly. So what sign would it be, plus or minus?
Plus.
Plus, exactly. And so even though in like math class we would never write a positive, we don't write +2. If we're just writing 2, we write 2, right?
Yeah.
In this unit, I think it's beneficial to put the pluses and put the minuses to keep your mind on track with fields that are to the right or fields to the left.
Gotcha.
So I put that very intentionally to indicate that's a right.
That's a right.
Rightward field, yep. And so now we would do the exact same thing for Q2.
I have a question.
Sure.
You ever apply this math to like actual hardware?
No, I didn't. I wish I did, because I think that would be fascinating. But that if you wanted to go, I don't recall actually which kind of engineering do you want to go into?
Aerospace.
Oh, okay. So I didn't know that. Is that new, or did you tell me?
I want to major in mechanical, but like.
Oh yeah, I don't think you ever told me that. That's fascinating. Wow, because that's my favorite field is space. Space is the reason I got interested in physics. It was looking through my brother's telescope when I was younger. Fascinated me, and knew I needed to learn more about it. And then as I continued learning more about space, I realized I really was studying physics. I realized everything that describes space is just physics. So I finally realized, okay, I guess I'm going to learn physics if I want to understand this. That's how it all started. That's great. Aerospace is going to be a booming field, I can tell you that. You know about SpaceX and Elon Musk and a lot of the private industries that are now going into outer space to either go to the moon or go to Mars or even service the space station, or they're even trying to, SpaceX, Elon Musk is the founder and CEO of Tesla Motors, who makes electric vehicles, and he's got his hand in a lot of different industries, and he's got another company called SpaceX, which now sends rockets to the space station to either bring astronauts there or repair the space station. That used to always be done by NASA, by federal government funds, and that's how the government controlled it. They always said private industry is not allowed to go to outer space. If you want to go to outer space, you have to work for the government, and it has to be through NASA. Well, as of a decade ago, finally all of those regulations were removed, and they finally said, hey, because 20 years ago, let's say you were a billionaire, and you said, I want to go to the moon. I have $3 billion. Can I go to the moon? Guess what?
You said no.
No, you can't go to the moon. If you want to go to the moon, I don't care how rich you are, you have to work for the government. You have to be working with NASA. But again, 10 years ago, all those regulations were removed, and anybody that's rich enough and has private businesses can now go into outer space.
Can now go, yeah.
And so that's when all these new startup companies started popping up saying, well, hey, rocket and make it go up to the space station, and I can bring astronauts there so that NASA doesn't have to do it anymore. And that's exactly what's happening. Over the last 5 years, SpaceX and other companies now bring all the astronauts to the International Space Station. It's all those companies are private companies, making tons of money too. But anyways, yeah, space is fascinating. So you might, depending on what you get in, if you get into mechanical engineering in the aeronautical, space program that you might go into, then you wouldn't probably do a lot with electricity. You do a little bit, but I was going to say if you were going into electrical engineering in any way, shape, or form, then you would get to use this stuff to design hardware like you were describing. Those are the people that use this, electrical engineers.
Yeah, I know that.
Yeah. Okay, so now what we do is, now what we do is just apply this to the second charge. I'm on the bottom right side of the screen now, and I'm writing E2, the strength of the electric field created by charge 2, will be however much charge he has, Q2. Remember, his field belongs to him. His field is proportional to his charge. right?
Yeah.
That makes sense?
Yeah.
And so now I'm going to just make myself some room here. I'm kind of running out of space. So now what we're doing is trying to work out this one right here, E2. How strong is this one going to be, right? And so we're just going to plug the numbers in. E2 will be K. We're just following along now with this formula here. Will be 9 times 10 to the 9th times Q2, remember, was 4 coulombs, divided by the same distance because it happened to be a point that was equidistant from both of the charges. So that distance again was 0.25, right, for 25 centimeters squared, right? And so now we recompute that one. So 9 times 10 to the 9th.
I got the answer. I did it all.
Oh, okay, divided by x, I get 1.44 times 10 to the 15th. You get that one for this value?
That's your full answer.
No, that's not the full answer. That was just his field.
Yeah, for 2.
Yep.
I
And,
got 5.76 times 10 to the 11.
oh, I keep messing up my storing. I'm sorry about that. Let me do that one more time. 0.25 squared stored x. Okay, trying one more time. 9 times 10 to the 9th times 4 divided by x. I don't know what's happening. Try again. 0.25 squared. Okay. I think I just keep missing the buttons and entering the wrong numbers. 9 times. No, don't do yours. Redo yours yet. Yours is probably right. Divided by x. There we go. I get 5.76 times 10 to the 11th.
Okay, yeah.
Okay, that was right. So let me just erase this. So what sign should that one be?
It should be negative.
Yep, exactly. And so we'll just reference that direction. Where is my pen? Come on, come back. There it is. So we would say E2 with a vector notation on the top will be negative, and that will be left. And then whatever it was, 5.76 times 10 to the 11th newtons per coulomb. I forgot my units on the other guy, newtons per coulomb, right? And so now to find the net electric field, we just have to add those two together. So I'm just going to erase this top part and try to finish that off. So now we finally get to apply this idea of net field. The net electric field as a vector will be positive 2.88 times 10 to the 11th minus 5.676 times 10 to the 11th also, which gives us
negative 2.88 times 10 to the 11th. Negative, yes, negative 2.88.
Yep. Where's my, there we go. Negative 2.88 times 10 to the 11th newtons per coulomb. That's the net field. And the negative is indicating it's to the left.
Got it.
So now, if we dropped 1 coulomb, exactly positive 1 coulomb of charge at that point, how much force will it feel?
Negative 2.88 times 10 to the 11th.
Yep, exactly. Because that's the amount of force that the net electric field is able to generate per, this is per 1 coulomb that you place there, right? So good job on that. So let me erase this and let me point out there's a new formula that you've been using that I just haven't shown you because I just showed you the concept first. So since we knew what E was, and remember I said that, let me actually move over a little bit. When I just asked you the question, I said, What if 2 coulombs of charge was placed there? What did you do?
Right.
You took the net field and multiplied it by what? By Q, right?
That's it, yeah.
So when I said, okay, if Q is going to be 2 coulombs, then you just took the net electric field and multiplied it by 2 in your head, right?
Yeah.
Newtons per coulomb. And look at the units, how those work out. Q is in coulombs, right?
Mm-hmm.
And the electric field is in newtons per coulomb. What do you get when you multiply coulombs times newtons per coulomb?
You cancel out the coulomb.
Yep, and you're left with
Just newtons.
newtons, which is a force, right?
Yes.
So that means the electric force can also be calculated by just taking the net electric field and multiplying by the charge at point P.
Got it.
So that's the charge placed at point P. And E net, remember, E net is the net electric field at point P. All right?
Mm-hmm.
All right. So I'd say, why don't you try 22? Why don't we start letting you try some problems now? I think you could try 22 and 24, and I can help you with it if you get stuck at any point.
All right. So, you know, I can use the equation for this.
Yes, I'm glad you recognized that. I didn't want to say it right away. I wanted you to think about it. Yes. The net electric force is equal to Q. Oh, can I show you one other very quick thing?
Yeah.
Just very quick. Let me just point out that if you look at what this equation is here, E net, and you just stick in the formula, K times Q over R squared for E net, right? And then you multiply that by, let's say, Q2, the charge you placed there. Whose law is this?
This is
K times Q1 times Q2 over R squared. Oh, whose law is that?
it's cool.
That's Coulomb's law. You see that?
Yeah.
So that just wanted to point that out. But yes, you can use the equation that's now right here on the left side of the screen for number 22.
I see.
So talk to me. What are you doing here? If I can just hear what your thoughts are on this problem.
I figured out what using that equation. I figured out what the equation gave. What the equation gave me, what it doesn't give me.
Okay.
That I have the force, which is 6.1 newtons.
Correct.
And I have the charge.
Correct.
Which is negative 7.3.
Yep.
What goes into the equation is that my goal is to find the electric field.
Yep. Good job.
It's like using simple algebra. I'm finding
Yep.
by dividing 6.4 by negative 7.3.
The only thing you have to be careful are those. Everything was correct other than units for the charge. Look closely at those symbols. It doesn't say 7.3 coulombs. There's something before the C. That's all right. That's called micro.
Micro.
Yep. And that means 1 out of a million of something. 1 over 10 to the 6.
That means 1 over 10 to the 6.
Yep, which is 1 out of a million.
But would it be exactly negative 7?
So we normally just refer to that as 10 to the minus 6. 10 to the minus 6 is the same as 1 over 10 to the 6.
So it would be negative 7.3 divided by negative 7. It would be 6.4 divided by negative 7 times 10 to the negative 6.
Yep.
I got negative 867,712 and 33.
So there's one thing I still haven't shown you, but so I'm going to show it to you soon. But for right now, what you have is right. 6.4 times. I haven't shown you actually. I'm just going to add it now. This equation over here is really that I've written is for magnitudes. So the magnitude of the electric force is equal to the magnitude of the charge times the magnitude of the net electric field. So those are assuming that everything's positive. Okay? So we're using absolute values for everything. And I'm going to show you a way of doing this in a minute. But numerically, you had the right idea. 6.4 divided by, and then the denominator will be 7.3 times 10 to the minus 6, right?
Not negative 7.3.
So because of the absolute value signs and what I just showed you, and I'm sorry I didn't tell you that before, we're just going to take positive values.
Okay.
Okay? And so let's see, I'll do that on my own here now. 6.4 divided by... All right, so I'm getting 8.77 times 10 to the 5th.
What are you getting?
I got about approximately 8.77, 10 to the 5th. Yep.
Yeah. Like I said, you gave me a more exact number instead of scientific notation.
Say again?
My calculation gave me a more exact number.
Oh, okay.
Yeah, but what you said is about right.
Okay. And so now I want to talk about the direction. Find magnitude, we did that, 8.7 times 10 to the 5th newtons per coulomb. But it says, and direction of the electric field at this position of this charge. So a lot of times you can solve the direction part of the question by just thinking about it. And I'm going to kind of describe that to you. So what you do is you think to yourself, it says that there's a point charge, a negative charge of negative 7.3 microcoulombs.
Yeah.
And it says that it's being feeling or a downward force is being exerted on it, right?
Mm-hmm.
So we know that if there's a downward force on it, which charge would be up here creating that field, a positive charge or a negative charge. And I still have to come back and talk to you about the difference between the directions of the electric field for positive and negative. I told you about the negative part. But just stay conceptual right now. Would a positive charge up here be pushing the negative charge down, or would a negative charge be pushing the negative charge down?
Negative charge.
Yes, exactly. So the negative charge would be repelling this other negative charge, negative 7.3 microcoulombs, right?
Yeah.
And so I'm going to show you this now. Let me erase this whole side. So I'm kind of cycling back to the beginning now. Positive charges have fields that go away, like this.
Mm-hmm.
But negative charges have fields that come in. Exactly. This is now all negative charges. Doesn't matter what kind of negative charge it is or how much physical negative charge. All negative charges have electric fields that terminate on them. It means the fields created by positive charges get drawn in and sucked into the negative charges. So all the electric fields end on them. They come out of the positive charges and they all end in the negative charge.
Yeah.
And so back to the bottom left side where I was just drawing over here, is that based on that idea, this electric field up here, this one, has fields that radiate away because they're always radially away. Erase that to not add confusion. I'm erasing that. So they all radiate out and away like this. But remember what we said, that which direction do those fields go? Up and up towards him, right? They always go in, right?
Yeah.
And so which way will that field be pointed as it goes through this point that we've been looking at right here? Would that field go upward through that point, or would that field go downward through that point? Upward, exactly. So one more drawing over here would show that our 7.3 microcoulomb charge that's negative had a force it felt that was down because it was being repelled by this negative charge. But which way is the electric field? The electric field at that point is actually up. So there's a rule, and I'm going to write it right here. And an easy to remember rule. In fact, I'm going to make pictures of it. So positive charges placed in a net E field always move in the direction of the E field.
Mm-hmm.
And I could demonstrate that here, right? If this was a positive charge, all of his field lines go radially out and away, right? At this point P, which way would his field go? It would go out to the right, right?
Yeah.
So if I drop a positive charge here, which way will he go?
Out to the right.
Out to the right, because we already know that he's going to be repelled by that other positive charge, right? And that's in agreement with this rule that I've written in the top right, that all positive charges in a net electric field always move in the direction of that E field, right?
Yeah.
The other part of the rule is that if a negative electric charge is dropped in a net electric field, it will actually go in the opposite direction of the net electric field. So I'll write that in for you here.
All right.
Negative. So this is a positive up here. Positive charges. And then this is negative charges placed in a net E field. Always move in the opposite direction of the net E field.
Gotcha.
It's always true. And let me just draw one more picture just so you say, oh, that makes sense now. Because if I go back here now and say, okay, here's our negative charge. all of the fields that he creates go towards him, like this, inwards. And if we looked at this point right here, which way does his field point? His electric field will point in, right? Right?
Yeah.
So if I drop a positive charge there, which way will it go?
Towards the left.
It goes to the left in the direction of the net electric field. Oh yeah, it's being attracted to that negative charge, right? Because positive and negative attract.
Yeah.
But on the other hand, if we say now let's put a negative charge there. Oh, I'm sorry, my eraser's not working. Come on. Now if we decide to put a negative charge right here, which way will it go based on this rule that we've just said? Negative charges go in the opposite direction of the E field, which will be which way?
To the right.
To the right. And then you say, oh yeah, he's being repelled by the other negative charge. You see that?
Yes.
So those two rules can be very useful for solving the problems that you're given, where they say determine the magnitude. You did that perfectly by getting the numerical value for how strong the electric field is. But often what you do is just apply these two ideas on the right side of the board that I've just written for you to figure out the direction.
All right.
All right. So why don't you try, so do you know the answer for direction for 22 then is which way? The
direction is going?
Yeah, the electron, remember, feels a downward force, which tells us which way is the electric field then?
Upwards.
Upwards, exactly. If the electron feels a downward force, it's going to move down. And if it's moving down, the electric field must actually be upward there.
Yeah.
Yeah. All right, so why don't you try 24? It's a little harder, but it's similar to what we did earlier. Yep, so you're going to want to, exactly. Good recognition there. You're going to want to use this one.
Yeah.
And you'll use it 2 times. Once for
the first.
Yep, I'll go ahead and label that Q1. And then you'll use it again afterwards for Q2. And then what do you do with those 2 values to get your net electric field?
Add them together.
Add them together, yep.
For the microcoulomb, so it'd be -8 times 10 to the 6.
10 to the -6. Yep, to the -6. Yep. Because remember, anything that's raised to a negative exponent is a number less than 1. Right? So like, let's say we said 10 to the -2. Well, what is that? That's really 1 over 10 squared, right?
Yeah.
Which is 1 over 100, which is 0.01. That's a number less than 1, right?
Yeah.
What if we said 10 to the -3? That's 1 over 1,000. That's really 0.001. That's a number less than 1. Anything that's raised to a negative exponent is a number less than 1, while any number that's raised to a positive exponent is always a number less than 1 or a number greater than 1. If it's raised to a positive exponent, like 10 to the 3rd or 10 to the 6th. Those are all greater than 1, right? Like 10 to the 3rd is 1,000, greater than 1.
Yeah.
10 to the 6th is 1,000,000, greater than 1.
Greater than 1.
So just remember that idea. Anything that's a small value, that's a fraction of 1, it'll be raised to a negative power. Anything that's a huge value, much greater than 1, is always raised to a positive power of 10. And can I say one more thing?
Yeah.
I'm sometimes sloppy with forgetting to point out that, like in the equations here, these are absolute values here. These are also absolute values. So you just use positive values to find E, and then you use the concepts to figure out which direction that electric field will be, and you assign plus or minus based on the concepts. So let me, like, for example, say this guy on the left is a negative charge. So which way will his electric field be at point P in the middle?
To the left.
To the left, yep. So that one would be E1. And then charge 2 is positive charged. Which way will his electric field be at point P in the middle?
To the right.
Remember, his fields radiate away from him.
Oh.
So his fields go outwards and away, right? Which eventually will go to the left as well. So are they going to fight against each other, or are they working on the same team here?
Working on the same team.
Yeah, they're reinforcing each other, and their fields are becoming negative direction. So when you're actually working out magnitudes, you just use absolute values. The absolute value of E will be proportional to the positive absolute value of the charges, and then you just assign plus or minus based on the picture that we just did.
Yeah.
I know it seems like, hey, you could have just put a negative in there, and it would have given you a negative value, but there are certain problems where that actually breaks down and it doesn't give you the right answer.
Okay.
So just trust my insight that it's best to just use the concepts to figure out the directions. And draw I would recommend drawing the pictures just like I did. Like, think it through. You know, I mean, especially when you want to go into physics, you can't just tackle problems without thinking about it. So that's a good practice anyways, to read it and then draw the picture out, really engage in the thinking, and then see, okay, those fields are to the left, and then you can work out the numerical value in magnitude, and there's the sign plus or minus based on the picture that you draw.
Yes. Really visualize what you're doing.
Yeah, I mean, at least I can't say that, you know, everybody's like me. I know that that's not true. In fact, I work with a physics teacher that is by far the brightest physics teacher I've ever worked with, and I don't think he visualizes anything. He doesn't draw pictures, and he's just very mathematical. when I ask him, if he does these things in his mind or anything, he says, no, I don't really ever look at pictures or anything. So, but he's a very unique. I think more people do like drawing pictures and visualizing things than people who don't do that. But if it works for you, I recommend it. Did you happen to work out what E1 is yet?
Yeah, I'm working on E2 right now.
So what did you get for E1?
I got -2 times 10 to the 7.
Why does this not work out for me each time? I don't understand what I'm doing wrong. Let me look at it again. 9 times 10 to the 9th. Did you put in 8 times 10 to the -6 for the charge?
Wait, 8 for -8.
Remember, you're just dropping the negatives out and just use positive values.
I put -8, but like that wouldn't affect the stuff.
No, that wouldn't affect the value. It would just give you a negative answer.
So instead of negative, it'd be +2.
Yeah, but the value for Q, was it other than the sign, was it 8 times 10 to the -6?
Yeah.
Okay, and what did you put in for a distance?
Distance I put.
Oh, did I mess that up? Wait a minute. Maybe I put in 6 by mistake. It's supposed to be 0.3. 0.03, right?
0.03. It's 6 centimeters, right?
But it's the distance from the charge on the left to the point P in the middle.
Oh.
Right? So it's true that it's 6 centimeters from one charge to the other charge, but you're evaluating the net electric field in the middle. And so it's the distance from the charge to that point.
Oh my God.
Yep, that sounds right. 8 times 10 to the 7th?
Yeah.
Yep.
I got the second charge. I got 2.6 times.
So what did you get E2?
Yeah.
So I'm getting 5.8, negative 5.8 times 10 to the 7th.
You're getting negative 5.8.
Let me look at it one more time just to make sure. 9 times 10 to the 9th. 0.03. You use 3 centimeters, not 6 centimeters, right?
Yeah, I changed it. Yep.
All right, so in the numerator, 9 times 10 to the 9th, divided by, 9 times 10 to the 9th, multiplied by 5.8 times 10 to the minus 6 for micro coulombs, divided by 0.03 squared. I get 5.8 times 10 to the 7th.
I'm getting the same answer.
Say again?
I'm getting the same answer.
All right, let's do it one more time. So in the denominator, we got 0.03 squared. And I get 9 times 10 to the minus 4. And maybe I don't know. It's very possible that every time I'm storing it, I don't know if my store button is sticking or something. Let's try again. 9 times 10 to the 9. And then times 5.8 times 10 to the minus 6 divided by x. Oh, my fault. Yeah, I finally got a different answer. 5.8 times 10 to the 19th.
I'm getting a 27.
I don't know what's happening what's going on. I'm going to do this one more time. 0.03 squared. Store that as x. Okay. 9 times 10 to the 9th times 5.8 times 10 to the minus 6. Enter. Divide by x. Now I'm getting my same answer again. 5.8 times 10 to the 7th.
That's probably me. Because you did something wrong.
So can you just clear your screen out?
Yeah, I'm doing that right now.
All right, so let's just do it one more time. So in parentheses, we're going to do the denominator, which is...
I did something wrong. Yeah, I got a different answer.
Oh, okay.
Yeah, I got 5.8.
All right. So now to answer their final question, which is, what is the net field? What will we do?
Add them together.
Add them together. So the net field will be E1 as a vector plus E2 as a vector. And just pointing out, what if you had 3 charges, 4 charges, 5 charges, 6 charges? Do they all have electric fields at point P?
Yeah.
Yeah. And what would you do to find the net electric field?
Yeah, them all.
You have to add all of them together as vector addition. And there's no guarantee they're all along the same line. They could be in any direction. So can you look at the top right of the screen for a minute? Jeremiah?
Yes.
Can you just look at the top right of the screen for a second?
Yeah.
You could have a point, and you could have E1 going this way. You could have E2 going off this way. E3 over here. These could be in any direction, right?
Yeah.
So you would have to break those all into their components and add all of the x components to get the net x component E field. Then you'd have to break, again, all of them into their components and add all the y components up to get the net y component E field. And then use the Pythagorean theorem to work out the resultant, the net electric field. So that becomes complicated. And then I did notice that your teacher is pushing you to do that. I mean, for me to do a problem like that, which I could do with you, but it would take probably a full hour, 40, if I'm going slowly so that I'm making sure the student is understanding. It could be 45, 50, up to an hour to work through a problem like that. And
I would have to.
Just pointing out, your last problems are like that. Which ones? I think, where is it? Yeah, like 30. Just 30, actually. 30 is the only one he really pushed you to do something like that, where they're at different points on where. And you end up with electric fields that are in different directions and different angles, and you have to break them up into X components and add all the X components together, break them up into the Y components. So can I just show you one thing here?
Yeah, go ahead.
Because I won't have time to do that with you, but I just want to just head you in the right direction. Let's say, for example, it was the problem, one of the harder problems, where it's charges at the corners of a square. They say that this is plus Q, this is plus Q, and this is plus Q, right? And now they call this point P, right?
Yeah.
What we'd have to do is do the same thing we did, it's just much more rigorous, but it's the same method. So you'd say there's nothing at point P, it's just an empty point in space, this one on the top right. And we just pair them out. We say this is charge 1, right here. We'll call this one charge 2, we'll call this one charge 3. And then one at a time, we'd say, which direction will charge 1's electric field be going through point P? Remember, this down here is point P. Which way would his field go?
Wouldn't it read all around him?
Yeah, but this is our point P right here. So which way will this charge 1, he's a positive charge, which way will his electric field be pointing at point P?
Oh, to the right.
To the right. So by pointing out, you use the same exact method, and you would draw that in, and you'd say, okay, that's E1. Which way will charge 2, which is the bottom left of the square, which way is his electric field going to be going?
Up to the right.
Up and to the right. Do you think it'll be, let's say they're all equal charges, Q, 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 they're all the same charge. Will E2 be longer of a vector, the same length vector, or shorter of a vector than E1? For Q2. For Q2, we're trying to figure out his electric field at point P. When we draw it as a vector, will it be longer, the same length, or shorter than the length for E1?
Shorter.
Because why?
It's further away.
It's further away, right? This is a further distance. So that would be our E2. And then what would we do for Q3? Which way will his electric field be pointing?
It would be upwards.
Upwards, right? And the same length as which other one?
Same length, the Q1.
As E1, exactly. And so before I erase this, your final answer for that last problem that we just were doing, it would have been negative 5.8 minus, what was the other one? 8 times negative 8? So it would have been negative 13.8 times 10 to the 7th. Because they were both in the negative direction, remember?
Yeah.
So just negative 8 times 10 to the 7th minus another 5.8 times 10 to the 7th would have been negative 13.8 times 10 to the 7th. So are you good with that problem?
Yeah, I see.
Okay, so now let me just point this out because we're running out of time. I only got about 5 minutes, and I want to show you this idea. So let's look at E2. Because do you technically know how to find E1 at this point?
Yeah.
Yes, his field is straight to the right. You can figure out how strong that field is because you just did that, right?
Yep.
So that one you already know. Do you know how to figure out E3?
Yeah.
Yes, you already know that. The one that we haven't done is how you do something that's on the angle like this, E2. Well, since it was a square, that number 32 is having you look at a square, number 30 is having you look at a square like I'm drawing here. This charge right here, this is the top right corner of that square, which we're calling Q3. I didn't mean that. Sorry, I'm taking that back. There's no point at that space. It's just an empty point in space. And Q3 is down here on the bottom left, and you told me his field will go up and to the right. Since it's a square, do you have a guess as to what angle this one would be right here?
Like 45 degrees.
Good, yep. So you'd have to use some trigonometry in conjunction with everything we've done so far. So what you would do is you would draw this as 45 degrees in here. And now, since it's up and to the right, it has some components. This component would be called E2 in the Y direction, and this component here would be called E2 in the X direction, right?
Yeah.
How will we find out what E2 in the Y is? Well, since it's opposite to the 45-degree angle, will that be a sine or a cosine for E2 in the Y? Does the opposite go with sine, or does the opposite go with cosine?
Opposite goes with cosine.
It actually goes with sine. So when you're finding E2y, it'll be the magnitude of E2, which, again, you would find E2 in magnitude by doing K Q2 over R squared, where R is now the distance all the way along this triangle from here to here. You'd have to do Pythagorean theorem to work out what that is. Okay?
Yeah.
So this R is this distance here. And you would get this as a number. Again, you've been doing that. And that number would go right here. But then you'd have to multiply it by the sine of 45 degrees to get the y component. How do we get the x component? It'll be the same thing, magnitude of E2 times which one? Sine or cosine now?
Cosine.
Cosine now, yep. And now, coming back to this mental picture here that I'm trying to have you see, is that to find the net electric field, you have to add all of the x fields together. Was E1 an x component field? This guy right here, is he all in the x direction? Do you see?
Yes.
Yes, because that was coming from charge Q1 over here and heading to the right, right?
Yes.
So you'd have to add E1 plus, who else in our triangle that we just drew? Who is in the x direction? E2x is in the x direction. You see that? So E1 would have to be added to E2x to get the net x direction electric field. Okay? How would we find the net y direction field? We'd have to add E3, because E3 is all in the y direction. It's right here. You see that?
Yes, I do.
E3 would have to get now added to the y component in the triangle that we just drew up of E2y, which is another little bit of upward, to provide us with the net y component electric field. So what we're doing is taking these fields and breaking them up into components that are along the x-axis and the y-axis to find out what's the net electric field in the x direction, what's the net electric field in the y direction, and that's where I'm at now. So this would provide us with E net in the y direction. And then for the final move, you would want to find out the net electric field. And so if these two pieces here, if E net in the y, if E net in the y came out like this, E net y, remember that E net y now comes from here all the way into our picture over here. Oops, I'm sorry, that's not y, that's x, my apologies, let me erase that. So if E net y came out as in the upward direction, E net in the y, which is this. And then let's say E net x was this way. And our E net x comes, you see where I am over here, like up here?
Yeah.
That's where we get E net x, and it would follow my pencil all the way down. This is where E net x would go. You see that? To find what's the net electric field is now the result. This takes you way back to the beginning of the year, which is vector addition. This hypotenuse represents the net electric field. So if you knew what E net y was as a number, and you knew what E net x was as a number, how would you get E net?
You would add them all together?
No, look at the triangle. We're in this triangle right here now. And let's say you have E net x as some number, like the number 12. And then E net y is some number, like the number 17. How do we work out how long the hypotenuse is?
Oh, you can do Pythagorean theorem.
Pythagorean theorem. Got it. So you would use Pythagorean theorem to work out E net. And then to find the direction of that net electric field, do you remember the inverse tan?
Yeah.
You remember doing inverse tan?
Yes, arctan, yeah.
Yep, arctan, exactly. So I know this is a lot to just throw on the page in 5 minutes, but I want you to have some shot at it. it's a hard problem. Like, it's a lot, but you could do it. But I just want you to know it's hard. And like when I do this with my students, it takes a while to get a good majority of the students proficient enough to do all these pieces and put it all together. So it's definitely challenging. And so the last move would be, what is the direction of the net field? So direction of net E field. Theta is the inverse tan, or arctan, as you said, of the net y component field divided by the net x component field. So E net in the y divided by E net in the x. From that picture, you'd have E net y and E net x, and you do inverse tan, and a number will pop out like 12 degrees or 75 degrees, and that will be the direction of that net field. I know that's a lot, but if you get to the problem and you have the wherewithal to give it a try, you could come back to my video and look it over.
I see, yeah.
I don't know, I wouldn't have expected that all that made sense to you because I was fast to go through a lot of parts. But remember, you can watch the video again if you needed to.
Mm-hmm. Yeah, thank you.
You're welcome. Let's see. Yeah, I think you have a reasonably good shot at doing some of the others. 30, that was 30, that's hard. But I think you have a reasonably good shot at trying some of the other ones because you got through 22 and 24 and 28. I think you could probably do too. So give it your best effort, and hope that was helpful for you.
Yes, sir. Yes, sir. Thank you very much.
All right. Have a good week, and I'll see you next week.
Yes.
All right. Bye, Jeremiah.
All right.
Bye-bye. You too. Okay, that concludes tonight's lesson with Jeremiah. Slightly past 9 o'clock, 2-hour lesson on electric fields.